Good morning, everyone. So I think the keynote from yesterday of Tim Lenton and Judith Gupta showed very clearly that to address climate change, we have to make some quite fundamental changes to our economy. And of course, it's only possible if you're actually able to predict the outcomes of different policies. So we are extremely fortunate to have Doyne Farmer as the keynote speaker this morning, who is a pioneer in complexity economics, which is perhaps the most promising approach to actually tackling this issue. And Doyne Farmer's work has been groundbreaking right from the beginning. So his PhD project at UC Santa Cruz was so innovative at the time about complexity science that nobody could be found to supervise it. So he found three colleagues to form the Complex Systems Collective to actually supervise them, supervise each other. And during this time, he and his colleagues also famously studied the game of roulette and built the first wearable computer to go on a sort of like semi-legal mission to beat the casinos in Las Vegas, to fund a kind of utopian science commune. So you would think at this point it's kind of difficult to top this still, but he managed to keep the momentum up. After his PhD, he went to Los Alamos National Laboratories, where he started his own group, the Complex Systems Group, which was one of the first of its kind, where he started even more focusing his attention to making complex systems models of economic systems. Then in the 90s, he took a break from academia to found the prediction company, which was the first algorithmic trading firm, which was again groundbreaking at the time and returned a profit 25 out of 26 years. It was in operation. Then he returned to academia at the Santa Fe Institute, which is the most renowned complex system science institute, where he continued his work. There's some debates here. We can talk about this later. All right. Okay. Was until he moved, of course. To continue his research, making complex systems models of financial markets and the economy at large. Then he moved finally to Oxford in 2012, where he's now professor and director of the complexity economics program at the Institute of New Economic Thinking. Of course, this little introduction does no justice to his career so far, but luckily he did the job for us by writing his most recent book, Making Sense of Chaos, which is part, I guess, autobiography, part introduction to complexity science, and also part advocating for complexity economics. So yeah, we're extremely excited to have you here and help me welcome Doyne Farmer.
Well, let me just say there's a little bit of exaggeration in that introduction. And also please, during the lecture, if you have questions, please stop and ask them. Doesn't do any good if you're sitting there confused. I'm here to help you understand what's in my presentation. So I always like to begin, well, let me actually just say the philosophy behind most of what I'm going to say. I'm going to start spending maybe 2/3 of the lecture on history. What does history have to tell us about climate change? What has happened in other technological transitions? And I'm going to begin with the history of the energy system. And then I'll talk about using simulation to actually model how the economy will respond. But let's start with the energy system. So here we have a history of the last 140 years of the evolution of the energy system that was put together by my ex-postdoc, Rupert Way. And so on the left, you have the cost. Sorry, I'm moving out of the camera. On the left, you have the cost of different technologies as a function of time. And on the right, you have their deployment. That is what fraction of the energy, of the useful energy, do they supply? And I should say useful energy is important because, you can measure energy different ways. Final energy is like how much could you in principle have extracted from it. Useful energy is how much can you actually get out. So it includes efficiency. So there's a little bit of crude estimation that has to go because it depends on exactly how you're using these energy sources. But still, so I want to also point out that the scale here is logarithmic, meaning it's in powers of 10. So each tick is a power of 10 larger than the previous one. And on that kind of scale, exponential increase corresponds to a straight line. So here you see traditional biomass, this green line that's roughly staying the same. Here you have coal, which is increasing quite a bit. So this is more than an order of magnitude larger at the end. Here you see oil and gas coming up, rivaling coal in about 1975, and then moving along with coal after that. Hydropower, nuclear power, biopower, wind, solar energy, lithium-ion batteries, and green hydrogen. So you see something quite striking, I think, in this, which is we have these new technologies like solar energy that are increasing at very rapid rates. Solar energy has been increasing, as you can see here, the rate hasn't really changed since 1975, been increasing at about 30% per year. Wind at about 20% per year. So we have very rapid growth. Now over here, we have the prices of these things. So let's again start with coal. Coal, once again, powers of 10. Coal, you can see it here, it bumps up and down. But if you fit a curve to this, you'll see that the trend is essentially flat. This is, of course, after inflation. But what it's telling us is coal costs about the same now as it did 140 years ago. Similarly, oil and natural gas, they bump up and down, but they all cost about the same as they did 140 years ago. In contrast, solar energy, this orange curve here, is coming down at a rate of about 10% per year and has been since 1975. So it's behaving very differently. Solar energy is now a factor of 10,000 cheaper than it was when it was first used commercially in the Vanguard satellite in 1958. In contrast, nuclear power here has gone up by about, this is US nuclear power prices in this plot, but it's gone up by about a factor of 3 since it was first used commercially in 1957. Essentially the same span of time, totally different behavior. So we're seeing something quite, we're at a very special place in the energy landscape now. You can see there's a lot of congestion in prices. By the way, this only goes through 2020, so we need to update it. But if we did, you can pretty much just project all the curves on the path your eye sees, which is also telling you something informative. But we're in a place where many different technologies are all competing at around the same price. And so there's a contest to see which one is going to emerge. So what I'm going to talk about in the first part of my talk is if we look at other technologies and then we come back to looking at this, what can we say about what's likely to happen in the future? Because of course, these are just historical extrapolations. It could be we get here and solar energy just goes flat, just stops going down. What are the odds that that will happen? So that's the first thing I'm going to talk about. And then we'll come back to say some others. As I said, please stop me if you, oops, it was working before.
Click on the slide.
What?
Maybe you have to click on the slide with the mouse and then.
Okay, right, let's do that. Yeah. Yeah. Well, traditional biomass, it's a little tricky. Traditional biomass is like people that live in the forest and build fires. But biofuels is stuff you grow on the ground, which could be wood chips. So, all right. Now, one of the places where I think science has failed us is in the economics of climate change. So far, all of the leading models, the IPCC integrated assessment models, the model made by the International Energy Agency, have dramatically overestimated costs and dramatically underestimated deployment. And I mean by orders of magnitude across the history of the transition so far. So here are examples. On the left, you see various projections that were made for the cost of solar energy. You see the data in the dotted black dots. You see forecasts in the year where they were made, going out to the year that they were made for. And so you see these forecasts, and you can see that even though there's a fairly clear trend here, somehow they're always underestimating how fast the cost will go down. I sometimes joke in my talks that at the IEA, they weren't able to plot data on semi-logarithmic scale in order to see the obvious trend that had been there for many decades when they started. And this is an example up here in this box of the rates of improvement they forecast in 2020, or these are forecasts reported in 2014 for what would happen by 2020. And you can see the rates were all lower. Not some of them weren't above it, all of them were low. Now that happened to also be a period, you see there's a period here where solar prices flatten out and then they go down sharply. So it was a tough place to make forecasts, we have to say. Forecasting from here to here, we had a very rapid drop, but it's still roughly on the trend line that they followed so far. Now, on the right, we see something from integrated assessment models. So I don't know, have you guys talked at all about integrated assessment models so far? So the IPCC, well, many people make what are called integrated assessment models. This started with Bill Nordhaus in already 1990, and he got a Nobel Prize for it. By the way, he forecast, his initial statement was that the optimal amount of warming for that we should tolerate was about 5.5 degrees centigrade. Now, why did he say that? Because in his macro model that he built, it's a representative agent model with one agent for the world. And that one agent is then trying to decide what will maximize the utility of the one agent. The measure of maximizing utility is consumption. And so he argued that 5.5 degrees would be the right number. He's now at 3.3 degrees centigrade. So he's still saying, yeah, let's go, let's do more. He got a Nobel Prize for this. And then that spawned a whole family of more realistic integrated assessment models that that basically try and model the whole energy system and economic system. They address the following question. If we had a benevolent dictator who could ensure that we followed the right policy globally, then what would be the least cost strategy to achieve a given climate target? So you pick the climate target, and then you model the cheapest way to get there, given that climate target, where you get to do everything optimally. And so they spend a lot of work optimizing everything as they go along. They also have to make a lot of assumptions. Like one of the assumptions they made, because when they first ran these models, they noticed that, oh, gee, so once they started putting in technology improvement, which they initially didn't have, when I visited the Potsdam Institute of Climate Change in 2010, they were just assuming all technologies improved at the same rate. If you looked at the picture I just saw last slide, that's very far from true. But okay, so when they first put in solar energy improving at 10% per year, they would see the whole model telling them do nothing but solar energy. Oh, that can't be right. So they put in floor costs. So they said solar energy can't go below a certain floor. So this is a floor. These are all various historical floors. I think light green is further in the past and dark green more recent. Anyway, you can see here, meanwhile, here is solar energy prices that have just punched through all these floors. So it's a very dangerous thing to make unvalidated assumptions when you're building a model, particularly if the whole output of the model hinges around those assumptions. Now, the other way you can think about this, if you want to think about deployment now for a moment, is to ask well, how fast do we expect solar energy to be deployed? Back in the slide back here, we can see it's been coming up roughly exponentially through time, but we know once it gets up to supplying whatever it's going to supply of the energy system, it will flatten out. So this curve will flatten out. And if you plotted this curve, these kind of curves on linear scale rather than the log scale I'm showing you here, then they tend to look like this. They're called S curves. They sort of look like an S if you exaggerated this a little bit. This is a typical functional form. That doesn't make sense to you, don't worry about it. But the other thing you can do is take the data, fit the data, and try and predict it. Now, this is blown up version of solar and wind, and these dashed black lines are what you get if you just fit lines to this data. And actually what we did was even simpler, just draw the line from across the endpoints. And so you can see, okay, it wiggles around, but it's roughly exponential. But as I said, if you plot the S-curve on log scale, what the S-curve does is it goes up exponentially and then it flattens out, roughly speaking. There's various nuances I'll maybe say a little bit more about in a moment. Now, here are some past attempts to fit the S-curves for solar energy and wind. Here's solar on the left, wind on the right, made at various points in time. You can see the dates in the legend. And the gray lines show alternative fits. And what's happening here is we march along year by year, starting in about, I don't know, 27 or something like that, and make a fit to the data so far using the functional form I showed you before, and then extrapolate it. And what you can see is, depending on which your end year is, the forecasts go all over the place, which is telling you these forecasts are not very reliable. But nonetheless, people have charged along and boldly made forecasts. So you can see them here. And so you can see that for solar, all of the forecasts fall well below what's happened since. Some of these forecasts, like this one, these guys incidentally work for Shell. Maybe they didn't have the biggest incentive to say solar was going to do big things. But so you can see their various forecasts here. Okay, that's this green one. They're all well below what solar's actually done since the forecasts were made. And so here's some other ones down here. And then here's wind. Wind's a little more complicated. Some of the forecasts are above, some are below, but you can see they're all very unreliable. That forced us to write a paper basically pointing out that these things were meaningless, in part because, well, I won't go into it, but let me just say that a lot of the work that's been done in this domain is really bad. And it's unfortunate because it's kind of an important problem. Yes. Yeah. Yeah. They were based on the historical data. So in other words, let's go back even one more slide. They took this data, although some of them, the first forecast was made in 2007, so they had data up to here. So they took this data and made that forecast by just fitting a curve to it, fitting the curve in this curve right there. That function, which has three parameters, the asymptotic level that the S-curve will flatten out up here, K, which is the exponential rate of increase down here, and T0, which centers the curve going left or right. They didn't say anything about the price. They just took the deployment or the cost. They just took the deployment data. They took this functional form with three independent parameters. They just threw it into their least squares algorithm and it spit out an answer. Okay, so very simple.
Why wouldn't you use more data?
Well, that's all the data we have. Or you could go back a little further in time. So maybe, I don't know exactly how far back they went in time.
I mean, the other variables which are like also
well, yeah. So you could also include prices. Now you have to have a more complicated model. And actually there's a problem there. This becomes a little technical because
Video.
All right. Becomes a little more technical because if you include costs as well, then so you have now two functions you're fitting, and those functions are interacting because really you have to think about the interaction of demand and technological improvement, and there's what's called an identification problem, meaning there's a whole set of parameters that can correspond to that, So you can fit the data, but when you go out of sample, the answer depends sensitively on this identification problem. So you still get forecasts that go all over the place. Though it would certainly be better to do that. And actually, we're in the process of trying to do that. But to do that, you actually need data where you get all the way up to the top of this S-curve, because on the exponential part, that's where you have the identification problem. You only begin to be able to distinguish alternatives once you see the technology start to flatten out. So, and for solar and wind, we don't have that data, which led us to say, actually already 20 years ago, we need to look at other technologies too. Okay, very good question. Thank you. Those are, people should be bold and ask your question if you don't understand what I'm saying. Okay, so now, fitting data to S-curves is hard for lots of reasons. So there's a reason, I mean, I have some sympathy that these things weren't very good, though people should have realized this. So first of all, the data is terrible and hard to come by. Even when you have the time series, you don't know how accurate the time series is. When you start digging in, there's a lot of garbage in the data. The time series are short. Solar, even if you take all the way back to 1958, it's still a pretty short time series. Growth is inherently a non-stationary process. There's an early phase and a later phase, so that makes it harder. Deviations from exponential growth are really small in the early stages. As I showed you, it's hard to tell. It looks like just noise around exponential growth. So how do you know when it's going to level out? The noise is heteroscedastic. So that's a fancy way to say that in the beginning, the noise is really small. In the middle, the noise gets big, and in the end, it gets small again. So you have to actually model the evolution of the noise as well. The noise is also autocorrelated. Turns out if there's an upward fluctuation that puts you above the curve on one year, the next year is also likely to be upward fluctuating. So that complicates it. And the fitting, as you saw with solar energy in particular, is strongly downwardly biased. So you have all these problems. Okay, and then show that again. Now, the question I'll address here is, and let me just say this is preliminary work with 3 collaborators, my graduate student Ben Wagenvoort, Joel Dyer, ex-postdoc of mine, and Francois Lafond, who is like my right-hand person for the last decade. And so does technological growth follow a deterministic law? So if the answer were, say, bacteria growing in a petri dish, which also follow an S-curve, we have a pretty good idea that, you know, there's a growth-death process for the bacteria. You can write down equations, and you can derive the law that they must follow. There's, of course, some noise because one petri dish is not the same as another. It also makes a difference, like, is it a stirred medium or is it spatial? So you have to get into the details of what's happening, but you can derive a law like the logistic equation. So that's one hypothesis. The other hypothesis is just one damn thing after another. You know, why did that dip occur in 2010? Well, that's when the Chinese got involved. So if you ask a lot of people, what's the reason these curves look the way they do? They'll go, well, this was happening here and this was happening there. And then there was the energy Wende in Germany, and you just go through all the events that happen. So both of these things are real effects. So the question is, how big are the effects? And of course, if you want to forecast, it's much better if it follows a deterministic law than if you have to anticipate that the Chinese, when they come out of the Cultural Revolution, are going to decide to get into renewables big time. Which, who would have known? Okay, so that's the question. And so, for example, if it follows the logistic equation, it says that technology should follow a differential equation like the one I wrote up there. And if not, well, we're stuck. So there's something in the middle. Now, what we did is we gathered a lot of data, and I can say this has been a big project because this data is very hard to come by. And we're now not just looking at energy technologies anymore. We're looking at, you know, list of things that are ammonia synthesis, steel making, cars, washing machines, nuclear weapons. So everything we could get our hands on where we could see how many things there were as a function of time. And it plausibly looked like it might follow an S-curve. For example, monasteries follow a pretty good S-curve. And we have to do some data cleaning because the data is a mess. So lots of caveats. And then we collapse the data onto a single curve. Now, how do we do that? we fit the logistic function that I showed you a moment ago, which has 3 parameters. We do what's called in physics non-dimensionalizing the parameters, which means basically taking everything so it's about the same, and we flatten out the S-curve with a nonlinear transformation. So meaning if everything followed exactly the same S-curve, then we would see everything lying along this dashed black line perfectly. So that's all you really need to understand. And we've set things up so that in these normalized coordinates, everything has the same center time, and everything has the same rate of growth, the same exponential rate of growth in the early stage, and everything flattens off at the same value of 1. Okay, so we're just kind of warping everything around to see whether the shapes are different. And so what you see is that, well, if you're talking about the logistic function, everything follows pretty much this curve up here, but there's an early stage where it tends to be steeper than it is later on in the exponential phase. And so, and different technologies hit this black curve at different places. But so anyway, that's complicated, but there still seems to be a pattern. At least once things get into this stage up here, you should be able to make some forecasts. You can see there's a lot of deviation though. So there is some evidence for the one damn thing after another hypothesis, but nonetheless, the R-squared values, if you know what that means, are around 0.9, meaning most of the variance is really explained by the S-curve. Now, but then we tried a different growth law, the Gompertz growth process. And when we do that, we see everything collapse onto what looks like a line. Now, that's this differential equation instead. And one way to think about it is in the logistic function, the rate of growth is equal, it's linear, but it's proportional to how much is there times 1 minus the rest of what's in the Petri dish. So as the bacteria start, there's plenty of food, so they grow at an exponential rate. But as they start to fill up the Petri dish, food starts to get scarcer, and so the growth rate slows down. So in the Gompertz law, what happens is growth starts slowing right from the beginning at an exponential rate. And this appears to give a better fit, but I want to put a star by it because now we're worried that we may have discovered a different law, which is that the exponential growth rates of technologies actually follow an exponential distribution. So we're trying to sort that out right now. I can never resist talking about the work that's in progress.
Well,
What?
so basically on this plot, right, it starts from -3 to 0.
Yeah.
Looks pretty good, right? And then it goes a little bit haywire.
Yeah.
Does it mean basically
I mean, up
that
here
the
it
same
goes.
exponent, they follow kind of the same exponential, but then as you said, the slowing of the growth rate is different? Or?
Yeah. Well, you're talking about this stuff up here going haywire. Yeah. So it's partly the way if you write down the solution, fluctuations are being amplified more in here when you make this projection. But it's also partly that the data is really crappy. And we're still doing this with pretty raw data because, you go through and you look at the data and you see things like suddenly there's a big jump. You're going along and, by a factor of 3 in 1 year. Well, is that real or not? So you have to kind of go look, did something happen to steel in 1923 that caused, so there's still a lot of garbage in the data.
Could it be on the right, more recent data, or am I?
Yeah, the more recent data is up here,
So that's,
but keep in mind, we have everything from monasteries, where the data ends in, 1500 or something, to railroads, canals, mobile phones. So now you start to get better data, but a lot of that old data is pretty bad. Okay. Now, one question, when you start looking at this, you realize a lot of the uncertainty comes from not knowing where the asymptotic level will be. You can see, if you look at solar and wind, they're going along, growing exponentially. The question is, where are they going to flatten out? And so it's hard to say from just the data we've got. But if you have a hypothesis about where it will flatten out, then you can make much better forecasts. And so this is saying, depending on how many terawatts of capacity you think will end up at. So for example, this is an IEA net zero scenario. And we ask, when will, if depending on your prior about where solar will level out, when will we get 80% of the way there? Of course, we can't say 100% of the way because that always takes forever, but 80% of the way. And so if it's the IEA net zero scenario, then we get there around 2034 or 5. If we're talking about, well, I should have actually put some other ones. Total electricity capacity is about here. That would be 2038. Total energy production somewhere out here, that's 2045. That's already telling you something pretty remarkable. If you think solar is going to end up going all the way there, we're going to get there fast. Very likely. These are, 1 standard deviation, 2 standard deviation, 3 standard deviation bands. So even with 3 standard deviations, we still get there before 2050. So in other words, this really hints that the transition is going to happen quickly. And I'll get to prices in a minute.
I don't fully understand what's the functional form of the prior here?
Well, you basically take the logistic function and you do some indirect induction to say, let's assume L is something along this axis. So you take L as a given.
And you do point prior.
You take L as a given, and then you fit the other 2 parameters. Okay, and we fit these other 2 parameters, assuming a model that I won't go into here that takes all those effects I said into account. Okay, and that we've shown actually fits the historical data pretty well. You can do the same with the Gompertz instead of with the logistic. It comes out pretty similar. Yeah.
So with the Gompertz equation, is that what helps you identify when the solar will flatten out?
Well, either Gompertz or logistic, you can still go along. You can still fit logistic, but you have to deal with this earlier data. Now, solar, from the data sets I've been showing you, is exponential all the way along. And that's the other thing we're seeing as we've looked into this more carefully, that actually some of the technologies just seem to be exponential all the way. I mean, and solar is an unusual one because we know exactly when it was first used commercially. So we have a complete data set. Most of these technologies, we don't know that kind of thing. Yes.
How do you determine what kind of technologies do you try to throw in? Because I mean,
Yeah.
be like a million of them, but you
We-
have to have some sort of comparability across.
We throw in any technology we can get. Like I said, and we're debating, we're trying to see how robust the results are to what technologies we throw in. Because as I said, we're treating monasteries as a technology. We can leave that out. The results don't change much. But and so we're actually doing a lot of robustness tests right now because we actually started with 1,000 different time series. And right away you throw a lot of them out because you see they're more or less the same as some other time series. And then sometimes we have to paste them together because we have this part over here and this part over there. A lot of times we see this is clearly way too incomplete. We throw it out. Or there's a gigantic jump in the middle. We throw that out. So we have to write down all of our criteria, make sure we can do it automatically so we're not data snooping. So we don't want to go through and say, oh, this is a really beautiful S-curve. We'll put the 15 best ones in there and then see what happens. So we do a lot of work to try and, well, yeah, criteria are, does it look like it got reasonably close to maturity? So we have some way of measuring that. Are there enormous jumps that suggest data problems? Things like that. Yes. Sorry, I couldn't quite hear.
I was thinking, like, for some of the technology, like washing machines, is like there is no technology, and then you're introducing technology, whereas like PV is like there are competing technologies.
Yeah.
So
80% diffusion in this context means, but let me first answer your other question because there's 2 different questions. It's true that one needs to worry that things may be different when a technology is genuinely new to when it's competing with a pre-existing technology. So for example, if you look at canals and railroads, canals are going up and they're just starting to, they're not completed their S-curve. Railroads come in and canals start going down. You also have to worry about stocks versus flows. Are you counting how many things were made in history, or are you looking at the rate at which things are being made? And that causes all kinds of confusion because the functional form we're fitting assumes things only go up, right? So there's a lot of difficulties to wrestle with in this problem. Now, but back to your question about this, what this means is let's assume, let me go back to functional form. Let's go back to this functional form. If we're doing a logistic function, L is the asymptotic level. The denominator of this equation asymptotically goes to 1. So asymptotically, X is equal to L. So what we say is, suppose we know L, because L is the problematic parameter here. Then we just fit the other two parameters, and we actually do this with more complicated methods, so we get probability distribution based on the noisiness of the data. Then we look when do we get to that date as a function of L? So L is on the x-axis now, right? So up here somewhere would be solar does all of electricity in the world at the present level. Double that would be, we double the size of the electrical system and we go up to here. But notice the dates don't change that much as we go along.
The total would vary, like one, it could be that the total demand of world energy use is increasing.
Yes,
That
right,
it also depends on the
Right.
distribution.
right. That's why we're putting it on the x-axis. You can choose which answer you like. Okay,
But it's x-axis. It's that the total demand as a whole is increasing, or just that solar percentage is increasing. It's like x-axis doesn't.
no, the x-axis is gonna, yeah, well, it just says how much solar there will be, okay, asymptotically, right? And now we're also dealing with other nuances. I mean, we're sort of plunging into the technical details that I'm worried might not interest everybody. But if you go back and look at that very first picture, what you see is global energy use has been growing at 2% per year for 50 years or more. Actually, almost across the whole 140 years. It's about similar. And so we probably, that's our default assumption, that energy will just keep growing at 2% per year. Now, of course, if the degrowth people get in, it might go down. I think that's extremely unlikely. Or, it might go up because, as I'll say in a moment, solar energy is going to make energy cheaper than it's ever been. So we may have a rebound effect where now energy starts growing even faster. Yes. They don't take into account anything. All we're doing is extrapolating the data. Now, so this is a very crude thing. On the other hand, it's so far been extremely reliable, as I think I'll show you. Well, okay. Let me just say, here is a prediction that lets this parameter L be free. But I put a star by it because we're still doing stuff to debug everything. But this is what we're trying to do. So we're actually attached probabilities. Each band is a 5% probability band. There's a 5% probability that it's out in the white space. But you can see you get up to a pretty high level here. You're talking about the order of capacity of 30 kilowatts. So that would be providing all of the energy. I'll come back and talk a bit at the end about the things you're worried about. Okay, let's move on to costs because, I'm already used up most of my 45 minutes. All right, what about costs? So now we're going to talk about this side of the picture. But again, we're going to look at lots of other technologies. So this goes back to, just to brag a little bit, in 2010, I published this paper in Nature where we said that by 2020, coal-fired electricity and solar would cost the same. People said, you're completely nuts. And, here was, here's a statement by the economist. 2014, solar power is by far the most expensive way to reduce carbon emissions. They said, you guys are just airheads. But all we were doing, how did I make this forecast? I took the data, put a ruler on the data, and I saw where it was going to go. It didn't have to be a genius. Okay. but we want to do better than that. So with various collaborators, the key papers were with Francois Lafond. We extended Moore's law and Wright's law. Now, what do we mean? Wright's law is learning by doing. It says that every time, if you have a technology following Wright's law, like solar energy, every time the cumulative production of the technology doubles, the cost goes down by a percentage. In the case of solar, it's about 30%. And solar's been following that all the way along. Or you can just assume Moore's law, which you have to realize is a remarkable prediction. You know, in 1960, when was it? 5, Gordon Moore said, based on looking at transistor density and integrated circuits, I predict it's going to double every 18 months. A few years later, he adjusted it to say every 2 years. That forecast has held true until now. So, and it's allowed people to plan production in a fairly dramatic way. I mean, my friend Alvy Ray Smith, was the genius behind Pixar, is also from New Mexico, so that makes us double buddies. They had the technology ready 5 years before they could actually use it and they said, look, just wait for Moore's law. We'll keep polishing it. As soon as Moore's law gets to here, we'll be able to make a movie where we actually simulate the characters with computers. And as you know, Toy Story was a big hit. So, okay, but that allowed them to get funding they wouldn't have gotten otherwise. So we came up with a method for making probabilistic forecasts, like the one I showed you for deployment. And we tested it by pretending to be in the past, making 6,000 forecasts for 50 different technologies. And we showed it worked well. So here's an example. This is a forecast for solar energy made in about 2013. So that's the last historical data point. These are the data points that happened since then being up to 2020. But if I had it updated to here, it would still be inside the bands. So you can see we're not just making a forecast, we're saying how reliable the forecast is. And all of our testing was about how reliable are the forecasts, because forecasts where you don't know how good the forecasts are, in our opinion, useless. Okay, so now what about solar? This is a paper with my graduate student, actually just finished graduate student, Leonard Baumgartner. And so here we see wind, here we see solar. And for this forecast, we disaggregated all the different components, like how much does the module cost? How much does it cost to install them? How does it depend on interest rates? How does it depend on capacity factors and all these different things? And what we saw is that for solar, the balance of system costs, that's things like how much does it cost to install it, have been going down at the same rate as the module costs across, many decades now. And so we forecast that solar energy is going to get to about $3 a megawatt hour by 2050. That'll make it more than a factor of 10 cheaper than any existing energy technologies. So we think solar energy is going to change the landscape. In contrast, wind, the balance of system costs have been holding steady, which means it should hit a floor at around $35 a megawatt hour. And so, it's going to get somewhat cheaper, as you see from our forecast, but not dramatically cheaper in the way wind has been getting cheaper. So that's our forecast. But it doesn't take any of the things you were worried about into account. So in the fast trend, we looked at a fast transition scenario. Key technologies are solar, PV, wind, lithium-ion batteries, and P2X fuels, meaning some kind of fuel that you make from hydrogen. You use electricity to make hydrogen, and you use hydrogen to make a fuel like ammonia or some other synthetic fuel. And we use that for things like heat, shipping, air transport, and so on. We assumed we had enough backup in the renewable energy that we could run the whole globe for 1 month. We phased out fossil fuels over 25 years, which is consistent with the other stuff I'm showing you. And what we showed, oh, by the way, this just shows you that this method of forecasting has worked well across the board. Here, these little bands are our 95% confidence levels. We stay inside the 95% confidence levels 95% of the time, as we should. And although P2X electrolyzers You can see it's more of a mess over here. This is the technology we're least sure about. This, by the way, was also the dominant cost in our scenarios. And what we showed is that a fast transition is likely cheaper than business as usual by about 12 trillion. There's a lot of uncertainty around that estimate. Why is it cheaper? Because we make energy cheaper than it's ever been. So even though we have to spend a lot on expanding the grid, we make energy cheap. The sooner we make energy cheap, the sooner we realize the benefit. So the net present value is higher. And by the way, it's $35 million more expensive if we had a nuclear transition. Okay, that's on this slide here. And for various reasons, I don't think small modular reactors are going to solve it. Now, I don't want to say that, oh, no problem, it's all going to take care of itself. We really have to work on energy storage. That's the weak point in the scenario we threw out. We really have to expand the grid dramatically. We have to somehow counteract fossil fuel politics that put crazy ideas in people's head. We have to make people realize the land use problems are really not that bad. Of course, you know, we have to get used to people have to get used to seeing windmills on the horizon and so on. But okay, my prediction is despite all these things, it'll get cheaper and we get all these other benefits: cheaper energy, low volatility of energy prices, energy security, low pollution, lower environmental impact, more sustainability, and most importantly, no greenhouse gas emissions. Now, okay, we do need better guidance. As I already said, the track record's poor. By the way, we've started a company, Macrocosm Inc. The idea is to scale up complexity economics, including this kind of stuff, but also simulations, reduce it to practice, make predictions day in and day out, because at the end of the day, the key decision makers are business people who make decisions about what they're going to do. And since we think the transition is going to happen quickly, we think most energy companies haven't really wrapped their heads around this. And so if we can make them realize that, we can spur them to make changes quicker. So because as my Alvy Ray Smith story shows, predictions influence what happens. Because they could predict, they could say, give us the money in a convincing way. Steve Jobs wrote him a big check and they managed to make Pixar. If they hadn't had that forecast, if there was no Moore's law, we wouldn't have, Toy Story would have been later. Okay, so, all right. So we're doing this with agent-based modeling behavior directly with bounded rationality, having the agents make decisions using either heuristics like trial and error, imitate the best, buy undervalued assets, etc., or putting in learning algorithms like using machine learning. Feasible information, we don't assume that the agents are optimal as the integrated assessment models that I mentioned do. And so we really try and get verisimilitude and we try and test our predictions. I should maybe stress that I already told you the question the integrated assessment models try and answer. We try to answer a different question, namely, what's likely to happen? End of story. And then how can we nudge it to make it happen a little better? And so this is something that's in progress right now. In this case, the agents are real energy and power firms. So there's about 30,000 of them globally. So we have 30,000 agents in our model. Each one corresponds to a real energy and power firm, at least in the initial condition. And then the way the model works is that each firm makes some prediction about the future cost of the technologies. They make a decision about how much to invest, which technologies to invest in. Then we simulate electricity markets and oil and gas markets to try and see how much energy each company supplies at what price, so we can compute their revenues, we can estimate their costs, we can then estimate their profits, and then we can go around the loop and do that year by year. And it's all conditional on policies for each country. So, so the model looks kind of like this. You know, we simulate the energy markets, we figure out how much each firm will invest, what they will invest in. Then we might have to create new firms as we go out into the future, or other existing firms may go bankrupt. we update the costs and we go around the loop and we try and do this about 20 years out into the future. This is energy generation. So right now, just energy generation, meaning all electricity generation, so hydropower, et cetera, oil and gas. We actually haven't done coal yet. We'll do coal eventually, and that pretty much, and nuclear power, that'll cover. Well, nuclear power is electricity, so that covers everything. And we have coal in there for electricity. We don't have coal for heating, but coal for heating is kind of no longer relevant. Yes?
Your prediction will allow energy companies to act on this. Do these kind of fossil fuel companies, or they want to know?
Good question.
You're predicting sort of like the absolute floor dropping out of energy prices.
Yeah. Yeah. They won't want the world to know. Yeah. But we're going to tell the world. So the world will know because of us. Now, but we will be willing to advise them on how could they make their strategy better, for example, because we're doing something nobody's done before, which is really putting in all the domain knowledge about how the energy sector really works. Most economic models don't have that kind of information in them. And secondly, we're simulating them and their competition. And each company is making some boundedly rational decision about what to do based on, and we're trying to mimic what they do. And one of the things I really like about this problem is that we have about 150,000 energy assets in the database. So we have a database that gives us 25 years of history for the global energy system. So we can see what's been happening. And our model is going to, because some of those existed at the beginning, but we have the order of 100,000 new energy assets that are installed during that period. We have to make 100,000 predictions that we can test. So the model's testable. And so again, we will have tested it. We'll know how well it is. We actually have implemented it right now for Canada, for electricity, Canada and Texas, actually. We've implemented Canada and the US for gas and oil for the world. And so we're now in the process of testing it. Once we are comfortable with the model, we'll build it out for the whole world. And I see a hand being raised at the back.
Yeah, I mean, two things. First is I'm interested to see if I can find a way to bring this to my government. Because
Oh, yeah.
the Canadian government.
Well, we can talk after the lecture.
Because
Yeah, we want to bring it to your government. Yeah,
But the other thing is that I refer to the Enroll simulation.
yeah,
Right? And one of the most scary things there is that no matter how we have the S-corp on any kind of energy transition, the only thing that really gives us the break to prevent the +3 on is to actually use taxes, carbon taxing.
Well-
like that. What can we say about it?
yeah. So I like the En-ROAD simulation. John Sturman's a great guy. I visited there a year ago. But I mean, it's a systems dynamics model. So when you look at something, you have to say, how much do I really trust this model? Even John will say, these models are hard to calibrate. How much certainty can John attach to that prediction? So we go head to head with him, and you have to really get in the weeds and compare the evidence of how much can you believe the model at the end of the day.
I mean, because the thing is that the way you present the transition
Yeah.
is ideal for places that are not willing to change their way of function.
Yeah.
Like, for me, it's difficult to make Canada behave like a network, right? In which the density and the energy consumption per capita is different.
Yeah.
So doing this allows you to carry on without necessarily changing technological use and energy consumption. It's great for places like Australia and Canada that are big.
Well, wait a minute. So it's not, we're just making predictions, right? You should, and subject to conditions like national policies. And this is just simulating energy transition. It's not dealing with the macro part. We have another model that does that. And so we can put in all those differences there, and we will build in the differences here. We look at the way does the energy system work. So if you look at Algeria, where I sailed the coast of Algeria 4 years ago, I can tell you their decision-making process is totally different. It's all from the top, and they could give a shit about climate change. we're going to take that into account when we're doing this, because it's policy dependent and state dependent. State-owned companies make decisions in a very different way than companies that are participating in competitive capitalist environments. So we'll look at each company and go, what kind of company is this? They're over here, right? They're making their decisions this way. Now, we can, of course, play with all that too. We're not saying we're just saying, subject to all of these assumptions, this is the answer we get. But we test it because we know in the past what the policies were. So we can say, if we knew the policies, then this is what would have happened according to our model, and we compare it to what did happen. So I think it's still going to be useful. I don't know what your country is, but it's Canada. Okay, well, why are we focusing on Canada in this model? Well, because some Canadians paid us to do it. But Canada has a big problem, in my opinion, because fossil fuels are the biggest export, and you know, even the Liberal government is talking a lot about carbon sequestration and storage, which in my opinion is a losing technology for sure. And so if Canada doesn't start changing what they're doing, Canada's in danger of really getting stuck in the energy transition. Okay, now I'm gonna show you an example of a simulation. This is like early stages, but the first one here, let's see if this works. Maybe I need to poke it with a mouse. Yeah, historical evolution, let's see. Yeah, here we go. Oh, there it's going. So here you get to see what Canada did. The year's up there. So the little drop things are gas. The little yellow atom things are nuclear energy. The black things are coal. Well, you can see it on the legend down there. You can see that's what Canada actually did during those years. And now let's go to the next slide. Now this is what our model says it will do without a carbon tax. Okay. So you can see, you know, you still get, well, even without the carbon tax, you still get a lot of wind and solar, but you get a lot of gas. And if you do put in a carbon tax, and you see also the final shares that all those investments have, if you put in the carbon tax, then you instead see the shares evolving like that. And so you come out with quite a bit more solar. Now, I want to put a giant asterisk by this because we haven't tested this yet. We're just literally right now getting our testing pipeline going so we can start testing. And one of the problems I have with existing models is, in my experience, as building first wearable computer to beat roulette or predicting the stock market, nothing works the first time you try it. Whereas the other models, they're not even testing them. If you can't test it, it's very unlikely to work, in my opinion. My experience is, if you want something to work, you have to actually test it and test it and test it. Yes?
Spatial data, like basically,
Yeah.
you know the information that there is a possibility to open.
Yeah. So this is a bit of a fantasy part of what I just showed you. We know where the existing power plants are. We put power plants near existing power plants, you know, in a 50-mile radius or something. Down the road, I mean, there are ways to plan this stuff, but that's a refinement on what we're doing. Right now, we don't care so much about that. Yeah. Yeah. I'm glad to hear that.
It feels like it can put energy producing companies out of business because there's grid management and there's energy production, and we can imagine energy communities really, you know, buying photovoltaics, buying storage, organizing themselves, and kind of creating these kind of little microcosms with this system, with if the forecast is correct.
That's a goal. Yeah, that's a goal. I want to be able to go, you know, the president of ExxonMobil and say, okay, we've simulated you here, and you can see we pretty much can estimate your profits and losses. by the way, if you've done this, you might have made a little more money, but you're going to go out of business in 2033 or plus or minus 3 years unless you get on board with a transition. That's my fantasy. I doubt that will actually happen, but I think we will be able to start engaging with energy companies and energy investors. What I've seen since my book came out is that we've had a lot of people coming over the transom, like the Canadian Pension Fund, saying, how do we invest? And so we will be able to, at the very least, tell these investors who to put money behind and who to short. And if the model really works well, we'll start actually making bets too and shorting these bad guys.
I was thinking, it's not just oil and gas, but like in France, there's like they're nuclear.
Yeah, no, so we want to advise, I mean, our ultimate goal is to advise policymakers, and whatever we do, I'm not going to do what happened with Prediction Company, where all the stuff we did just, made some Swiss guys rich. Okay, it made me a little bit rich. And, but, did it do any good for the world? No, nothing. So here we're going to make sure that at least there's an open source version of some kind. We may have a premium version that's better, but, and you had your hand up and then you and then you.
Related with because there are a few agents that are modeled, so is like kind of small scale individual PV option also included, or is it just including the utility solar?
We're right now just including utility level solar. We are talking to a data provider who may be able to give us with residential solar data too, and we will certainly put them in there too if we can have the data to test that. Yeah, that's true. That's true.
Perhaps like the portion issue is that we have more decentralized.
Yeah, we may end up with a more decentralized power system, and that would be very interesting. It's going to be more expensive, but makes people feel good to have their own ability to do that. Yes.
Do you not include energy storage in these models?
We have energy storage in there. This simulation did not, but we have it in there now. How do we think about demand? Right now, we think about it by getting somebody else's demand forecast. So we get one from the IEA and we plug it in. Down the road, we'll be making our own demand forecast, one step at a time. Over there and then back to here.
But my first question was related to storage, and the second one is really how can we take into consideration the climate hazards, the unexpected evolution. As you've said that you put the power plants next to where existing power plants. I've had cases with energy companies in the US, for example, where they had to review their capex to increase the gas compared to renewables, only to ensure the reliability and the access to their clients' activity of business, because the wind turbines couldn't run the same amount of months as they did before, because the climate is changing.
Yeah, so we're not taking into account changing climate right now. We can try and do that in the future. I don't think that's a first order effect here, it's a second order effect, but it could be important. We are thinking about physical climate risk actually with another model I'm not talking about here. We built a model to predict the economic impact of COVID in the United Kingdom. It was essentially a supply chain shock transmission model. And so we're applying that now to natural disasters. We actually have a Japanese client that's an insurance company in Japan. We're helping them build a model to better price their supply chain risk insurance by taking into account all the second and third order effects. Plant here gets damaged, their product now can't be used by lots of other plants that aren't damaged. And so you have to model the cascading failures, which is going to become, as we have more and more physical climate risk, a bigger problem. For right now, in the short term, I think transition risk is still much bigger than physical risk. That is, unless we do the transition in a sensible way, we're in danger of suddenly discovering, oops, we actually decommissioned too many fossil fuel plants too quickly. Oh, now we don't have power. So we do want to make sure that power stays steady. People are going to get very unhappy, as we saw in Spain a couple of days ago. If they don't have power, we've got to do that. It's actually important to realize that I think we will end up having, probably to begin with, gas-fired turbines or turbines burning some fuel to back up almost the whole electrical system. And you might go, well, then why are we building the renewables? Well, because first of all, gas emits carbon. Secondly, it's expensive. Most of the cost of gas-fired electricity is gas, not the plant. So it's actually very cost effective to build a gas plant and only run it 5% of the time, and the other 95% do it with renewables. That generates electricity cheaper, much cheaper than just running the gas plant. And then we phase out gas. And hopefully we don't have to build 100% gas. By the time we get there, we can really have ammonia and other zero carbon fuels supplying the backup power. But if we could get 95% of energy emissions clean, we'd already have made big progress.
A quick question on what linked to experts. Does it necessitate more investments from the company? Just like
Well,
if running a gas plant or
Yeah.
you have like turbines,
Yeah,
can we ask them to have new technology in order to be able to run the turbine?
right. So it does necessitate more investment because you're building more stuff. So there's more CapEx and less OpEx, you know, that kind of jargon, more capital costs, less operating costs. So you have to do the comparison right. You have to amortize the investments. Pardon?
Asking as a Swiss investor.
Okay, good. Well, we want you as our client. But yeah, so you really do have to try and compare apples to apples by looking at what's going on with the investment cost. Fold it in. You know, one of the pieces of good news is actually investments going on all the time. There's often these headlines of, oh, we need blah, blah investment to do renewables, but they don't say, well, you know, we're normally investing 4 trillion a year for energy, and maybe that has to go up to 6 for a while. So it's not a radical change, actually.
And promise this would be my last thing. So that like the example I gave you was really practical one.
Yeah.
That, for example, the regulation, in order for fund to be sustainable, we needed to select some energy companies that has only more than 50% of green CapEx.
Yeah.
But this company in the US, they had this issue of like continuity of business. So they had to review their CapEx
Yeah.
and reduce the renewable and the gas for continuity of business. So I had to short them from the fund. So it resulted in financial loss. This basically my question is how we can make a better assessment of energy companies in order to ensure the continuity of business, but also to increase the share of the green CapEx.
Yeah. Well, you know, we want to set up our model so you can give us your questions and we can run the scenarios that you think are interesting, and you can see what we think will happen. Yeah. So you had your hand up?
Yeah, thank you. So you mentioned boundedly rational agents,
Yeah.
right? So I was wondering if you model this adoption implementation gap in this model, like the because bounded rational agents will adopt a technology and then there is this decision-making gap where it will be implemented.
Yeah.
So with the temporal scale, I was wondering if that was implemented.
Yeah. So, so these things are difficult, and we're testing various hypotheses about how decisions are actually made. You know, for one thing, if you're ExxonMobil, one reason you don't just become a solar energy company is, what is your intellectual capital in your company? You've got a bunch of petroleum engineers. They don't know anything about solar energy. So if you're going to become a solar energy company, you have to probably go out and acquire a solar energy company and try and build that, right? Because you can't really make a right angle turn, and you have to start firing your petroleum engineers. It's hard to do. So that's actually one of the hardest things for us to model, is this increasing returns to scale, to specialization, and the institutional culture, which is very important in making these kind of decisions. But it's not impossible, I think, to do this. Right now we have a parameter that has to do with the stickiness of the of the strategy. If if it's sticky, that means you're just going to keep doing what you're doing. And in fact, one of the things we've been looking at historically, what's happened so far, most companies only have one technology, and what technologies do they invest in? That same technology, end of story. So it's just a question of how much they expand. And it's also a question of, if it's a commercial market, how much selection pressure is there based on profits? In regulated markets, the selection pressure goes away. And so those are actually the hardest ones for us to model. That's one reason why I said we've done Texas. Texas is a nice, clean, isolated electrical system, and it's a competitive market, very easy to understand. I'll come back to you in a minute. Okay.
Yeah, it's a bit related to the past two questions. So there was this panel discussion about Vattenfall once, and I read the annual report, and they said something like, "Oh, we're scraping this offshore wind development because of the high investment costs and the returns. The profit is not as high, and so on." And it comes back to this question of private companies are not necessarily interested in providing cheap, abundant, clean energy, but making a profit. Right?
Yeah.
Or Shell says, "Look, we want to go for lower and lower carbon, but it has to be profitable."
Right. I would they want to make a profit.
Yes.
And maybe they want to do other stuff.
Exactly.
Yeah.
Yeah. So I guess my question is it's similar this Brett Christopher's kind of thing. The price is wrong. It's not really the cost that's important, but the profit. I'm wondering how you take that point, and I guess you could say, look, I don't actually care in this modeling because first of all, I only make predictions, and second of all, I have the policy landscape. So I guess you address it actually in the modeling.
So we tell them, we would say to them, what do you think are likely policies to be adopted over the next 20 years?
Yeah.
So let's put those policies in, let's see what happens. Or they might even say, what happens under this scenario or that scenario for policies? Now, my ex-graduate student and postdoc, Penny Mealy, who's now at the World Bank, she's used large language models to create a taxonomy of policies, climate policies. And the taxonomy actually allows her to make some predictions about policies. So she can even make predictions, given this is country of this type, these other countries with political systems like this have adopted these kind of policies. So we can even down the road make some predictions about what we think the policies are likely to be. But of course, people who are on the ground and really understand the climate may have better predictions.
But I guess you take that point, I'm interested in profiting, we have to create policies too.
Right, right.
There's no
and of course, they're dealing with they're in an environment where it depends on what country you're in. If you're Russia, you're probably not worrying about green policies. If you're in Holland, I think you are, right? So, and we aren't probably going to be advising the Russians anyway. Although, actually, I think the Russians should be worried about it for the same reason Canada should be worried about it. Because if your economy is fossil fuel based, you're not going to do well in the future if we're right, and the transition is going to happen quickly. Yeah. Yeah. Good training.
I have a question about what do you make of these climate finance and international conferences and obviously country policies, because as far as I've seen, you obviously think of the private sector as companies and firms, innovation and energy sector, but I usually see the green transition as something that will probably happen because of green policies or countries following a path. And but when we see what happens at COPs and so it seemed like there are these countries just pointing at each other saying oh, everyone is kind of behind, and then you have this the new collective finance goals about financing each other or helping each other transition, but it's way below the targets, or I don't know how much you follow that.
No, I follow. I think I hear what you're asking.
And so I'm just, do you have any comments on
that? I do. First of all, predictions can make a difference. They can change the world. I was very happy to see that even Boris Johnson, of all people, at the COP in 2022 or whenever it was, when our paper was coming out, was quoting the numbers from our paper saying we need to get behind this. We're going to be leaders. We want to be leaders because we want to change the narrative. The narrative has been, as you're saying, climate change is a hot potato. We got to pass it around. Nobody really wants to hold it. But we're saying, look, it's a business opportunity. If you want to have your economy thrive, it's going to happen. You better get on the train because it's going to happen. Now, of course, that, you know, I'm not sure Putin's going to believe that narrative yet, but Boris Johnson believed it. And that was a good thing for us. Now, you know, his replacement, Sunak, he backed off on it. But so it does help put some pressure on the decision makers to do that. But I think the good news that we're arguing is some of this is going to happen automatically just from economics now. We're far enough down the learning curves of solar and wind and they're different enough than fossil fuel technologies, which remember, have not gotten cheaper for 140 years, right? And I don't think there's any reason to believe they're going to get much cheaper in the future. Now they may get a little cheaper because as demand starts winding down for natural gas, for example, then the supply is still big, the price is likely to go down. And we can model that in our model. So,
Like the industry and the
I mean, okay, it's a big problem, but on the other hand, I think right now, let me actually say something else in response to this. You know, there's a lot of pessimism because we look at it and you see article after article saying fossil fuels, they aren't really going down yet. Things aren't really changing because emissions aren't going down. True, but S-curves are exponential and exponentials surprise you. So if you have an S-curve that's growing at 30% per year, it's small, and then suddenly it starts getting big. And when it gets big, the derivative goes up exponentially with the level. And so they are late to appear on the stage, but when they appear dramatically. And we're just at the stage where we're seeing that happen now. Solar is, I think, depending on how you count it, 1% of final energy, maybe 2 or 3% of useful energy. And, but, you know, in the US last month was the first time renewables generated more electricity than fossil fuels. Investment in renewables is bigger than fossil fuel investment. We're right at because as one S-curve goes up, there's an inverse S-curve that goes down as the competition is driven out. And so we're at the point where we're just starting to see that tipping down. And because of the 2% energy growth, it's distorted. So fossil fuels will keep going up. But people, you know, like Vaclav Smil will tell you, energy never goes down. All sources of energy keep going up. I come back and say, well, what about whale oil? Oh, okay, well, we're not going to count whale oil. Whale oil used to be a big source of energy for lighting. But okay, so I think once we really start to see it going down, once renewables really are at 50% of energy generation, then they will have a much bigger revenue stream and their lobbying will get bigger and they can really start to go head to head with the fossil fuel companies. But we've got to get there. Sorry, I'll come back to you, but new people first. Okay, I'll do her first and then you.
The different rates, different pressures on the energy transition in different countries interact. In the same way that we had a talk yesterday about developing countries have different priorities and speeds and challenges with the green transition. Like, how does that interact?
Yeah. Well, I think it's to be determined largely. I think that one of the virtues of the model we're building is we'll be able to play out different scenarios. And so you can say, well, suppose your country adopts this policy and these other countries adopt these policies, what will happen? The scenario I hope to show, echoing what I said a moment ago, is the get on board scenario. If you don't get on board, you'll be left behind. Interestingly, I was in Abu Dhabi a few months ago. The Abu Dhabians totally understand that, you know, they're not going to pump oil forever. And they're really very, very interested in how do we keep going? How do we make sure that we don't go back to being so poor nobody wanted to even colonize us? Which they'll say, you know, we were so poor, they didn't even bother with us. But they're really thinking about it. You know, they really want to direct their country into the modern world. And so that's what we hope to help advise people about.
Yeah, you mentioned that predictions have a real world impact, and that's also your hope here. You just said it again. I was just wondering, maybe just taking it too far, whether you also have some scenarios that actually kind of model this kind of feedback loop that the impact you might have, because then it kind of gets accelerating thing that people are following your predictions, and then it gets even more bold and so on. So then I was wondering whether you consider that, or whether you think that's too far out there.
So let me make sure I understand the question. You're wondering whether we can model ourselves?
Yeah.
Yeah. Down the line, yeah. No, it's possible to do those kind of things. I mean, I have a paper called The Reality Game where I look at what happens when you have self-reinforcing prophecies or self-defeating prophecies. And what you see is that there's still an anchor in reality, but you can actually amplify what really happens, as in my Alvy Ray Smith story. Okay, sorry, do you next?
I was wondering, do these predictions already incorporate developments in AI? And if not, how do you imagine those will impact the transition, given that they obviously have potential to produce efficiency gains, but also to bring with them power dynamics and efficiency gains in the fossil industry? Yeah, so they're not in there yet. That's something down the line we'll try and put in. But we're certainly thinking about that. Of how it might net? Yeah, well, AI, I'm not, to be honest, I'm not very good intuition. I think it can give some efficiency benefits. The rest is not quite so obvious to me. For, you know, running the electricity system, I mean, there is already AI in there in some markets, because I was an advisor to a company called Invenia that was doing electricity trading using neural networks. So, I mean, that does make the electricity system more efficient, because they provide better predictions for what's going to happen next. But that's more of a second order effect, I would say, than the first order effect. We'll see, might get bigger. Yes?
My question is related to a question that there was before about the materials and the mini.
Yeah. So let me go forward a couple of slides and I'll address this question, and then I'll wrap the talk up. Okay. All right. Okay, we have a macro model. I'm not going to talk about that now.
Can you please come
back? Okay, you wanted this one?
Yeah.
Okay, it's in our paper too. You can just take a picture there.
I think we might get the slides also.
Okay, I'm happy to give you the slides. So let me just show you this slide at least. So we're really trying to build an sort of a integrated climate economics model. We have the energy investment model that I just told you about in the center. We have demand side model we haven't built yet. We have technology cost forecasting models. I talked about that a lot during this talk. We have our macro model. I just flashed that. We have a labor market model that Ria Del Rio Chinona has been leading, which basically forecasts how occupational labor responds. How do we get the workforce we need, the skills we need, and how do we deal with stranded labor? Policy feasibility model, I mentioned that Penny Mealy has built, that basically asks what policies are likely to be politically feasible given this. So we're really trying to model the whole thing, building it out, testing each module separately, but then plugging them together. Right now, we're just managing to plug. When we have these two plugged together, we're going to plug these two together soon, and one step at a time. Now, you asked me about minerals and so on. Well, the same thing we're doing for energy, we can do for mining. So this is not in the picture here yet, but we also want to get mining in there. There's actually interest from the mining industry. So I think mining is a very good candidate for this kind of thing. And we want to go downstream to electric vehicles. So upstream to mining, downstream to electric vehicles. So we really want to expand out to do more and more of the economy. Our long-term goal is to do for economic planning what Google Maps did for traffic planning. We'd like to have every company in the world in our model, and we'd like to be able to look at their inputs and outputs. And if that company says to us, well, how should I be thinking about my strategy? We want to be able to inform them about what their environmental impacts are, how they could become more sustainable and how they could make more profits. And by the way, we're in the process of becoming what's called a B Corp, a public benefit corporation, so that we don't have to just maximize value to shareholders. You had a question as well.
Drill JB drill. And
Yeah.
the willingness to the American.
Yeah. Yeah. Yeah.
based on
Yeah. Well, besides just moaning and, we'd like to be able to model that. I mean, if we had been able to model tariffs, then, we would be able to be making statements about that. We're not quite ready yet. And certainly it's quite clear that drill baby drill is just a stupid strategy. It's gonna, even if you really believe climate is a hoax, it's still a really stupid strategy because it just makes energy more expensive. Now, Donald Trump could, yeah, right. So, stupidity, we can put it in the model as a scenario and show, look, guys, we don't think it's going to help. Now, whether that will make any difference or not, I don't know. It's probably not going to change. I'm sure it's not going to change Donald Trump's mind, but it might change some executives' minds who are more rational and, are concerned about their company going forward in the future. Now, we had an article in the Wall Street Journal that basically saying that while Trump is obviously it's a bad thing for the energy transition, it's not a fatal blow. The energy transition is going to keep going on without him and without the U.S. U.S. is only 30% of the emissions, but, and we'll see what happens 4 years from now. Does the U.S. become a fascist country or does it go back to democracy? We'll see. Don't know. Yes.
Quick follow-up question on American policy and then one on energy substitute, like stacking versus substitution.
Yeah.
So I live and work in Louisiana and they're very into carbon capture and sequestration.
Yeah.
Got the industry on board. They got National Science Foundation on board. You mentioned you're bullish on it or bearish on it.
Yeah,
could you
bearish.
share a little bit more about why you think it's maybe not a good investment?
Sure. Sure. So carbon sequestration and storage, everybody probably understands the idea. The carbon's coming out of the smokestack, you grab the carbon and then you stick it into the ground. And so first of all, it assumes that as a lower bound, you can ask, what's the cost of the underlying technology that's producing the emissions in the first place? So if it's gas-fired electricity, well, what is the gas cost? And if solar is cheaper, by quite a bit, then you might wonder why you would be doing gas in the first place. Secondly, carbon sequestration and storage only gets typical projects so far extract 50% of emissions. Well, is that going to be good enough for an aggressive carbon reduction scenario? I don't think so. Now they say they can do 90 and they're really optimistic, but so far, even in best case, they might get 70 or 80. So I think that's a big count against it because if you're going to make a bet on CCS, you're making a bet that the transition is going to go very slowly and that the competition is going to remain expensive. And that, the intermittency problems can't be solved and so on. Whereas I think, if the gas is only running 10% of the time or 5 or 10% of the time, then CCS becomes less important. All you're doing is you take 10% to 5%. That's what you do with CCS. It's expensive. And then there's also the problem of injecting it all back into the ground, which I think the problems are, that's a very controversial topic. Some people will say, no problem. Other geologists will say, actually, we're going to pump that much carbon into the crust. We're going to have problems. So
my follow-up question is on the French philosopher book More and More and More, which talks about the idea that there hasn't really been energy substitutions, but rather energy stacking. And I'm curious, thinking about those different costs, even when maybe costs of other fuels have been lower, it seems like usage continues. So why in the case of solar would we expect that maybe a full substitution rather than a stacking?
Yeah, most energy sources have been of comparable cost. And as I said, some have gotten phased out like whale oil. So it's not that these things never happen. The uses have changed. Gas used to be widely used for lighting. We don't use it for lighting anymore, so that use went away. That, I think, yeah, we still are using traditional biomass, but it's hard to even measure, and I actually think traditional biomass is going down more than that plot showed. But, yeah. No,
Quick note on the time.
Yeah.
Like maybe 5 more minutes. You
Okay.
decide whether you want to do
it's up to you guys.
questions.
Well, I think, let's see, I might have had, let me just see if I got, all right, I think I've already gotten this across. I'll just show a picture of my book. Everybody, please buy at least 100 copies. Okay. Oh, wait, I saw some new people asking questions. Yes?
Does the model basically implicitly assume that everything else is basically equal? So the cost of fossil fuels and materials that's needed to produce or to construct this huge new capacity effectively stays pretty much in line with where it has been in the past, and this is like geopolitical issues regarding getting access to these materials.
Well, we try to break all those things down, so they're in there, and we can see assumption by assumption what makes sense. We do have a model of oil where mostly what the model does now is it says, if oil is at this price, how will all the producers of oil respond? But we'll build a demand side. We want to build a better demand side model. We want to build a model that can incorporate as many of those things, as you said, without making assumptions about it. So, but it's obviously a lot of challenges to address in there.
Maybe one last question.
Yeah.
So thanks. You mentioned using simulation models to test various decision-making models of agents to see which one fail or doesn't rest the data.
Yeah.
So here I was wondering, once you move to the level of individuals, away from companies to individuals, how do you deal with the humanity in decision-making rules that?
Yeah. Well, we start by looking at a lot of data. In our macro model, for example, so there we're modeling households, and we have synthetic households, and we'll make a couple of million individuals that we organize into households, and some of those individuals have high education levels. The individuals have an age, gender, race. So we have all of those things in there. They're synthetic individuals, so we're not dealing with real individuals, but we try and demographically match the whole population. And then we look at data on how they behave. So we right now are improving our model by building a better consumption model. So if you're in this demographic group, your consumption is different than if you're in that demographic group. Now, of course, the consumption patterns could change over time, but at least we start with a baseline that's fairly realistic.
Some individuals being more rational in the sense that they take into account costs and
Yeah. So our goal is certainly to do that kind of thing. There's even, you want to model, there's some individuals that are just natural early adopters. As soon as electric cars come out, they're going to go out and buy an electric car. There are other individuals that are going to be very slow to adopt. And so we can put in that kind of stuff, again, making use of what's known. This is where there's actually a very useful marketing literature about consumer behavior. And there are models marketing people run already that do this kind of stuff. So we don't have to reinvent the whole thing.
Okay, we have to wrap it up here. Thanks so much for an excellent.
You're very welcome.